Все. Okay. Last time we discussed the Hecke algebra, and I shortly recall you some facts about this algebra. Hecke algebra Hn of Q is finitely generated and finite dimensional algebra with generators G1, Gn minus 1. These generators satisfy the braid relations of the form and the generators standing far from each other are commuting if and the last relation is a Hecke condition. For any generator, its square is a linear combination of the unit and where lambda is q minus 1 over q. So q is a parameter, non-zero complex number. This is a definition, and it turns out that this algebra is finite dimensional and if the parameter q is not a root of unity, that is q to the kth power is not equal to 1 for any k is equal to 1, 2, and so on. This is a semi-simple algebra which is isomorphic to the group algebra of symmetric group. In this case, we have an isomorphism of Q is isomorphic to the group algebra of symmetric group. And as any semi-simple finite dimensional algebra, this algebra is isomorphic to the direct sum of matrix algebras, of finite dimensional matrix algebras. And this isomorphism is the same as for the group algebra of symmetric group, namely Hn of Q is isomorphic to the direct sum. And these matrix algebras are enumerated by partitions of the number n. Mu is a partition of n, and here is a matrix d mu. The dimension of matrix is equal, I denoted this dimension by symbol d mu, and this d mu means the number of standard Young tables corresponding to the diagram mu. If I have a diagram mu, for example, for mu partition of 3, I have, for example, the diagrams corresponding to partitions of these types. These three types are only possible partitions for 3, and in order to get the Young table, I should place in the boxes the numbers from 1 to 3 in such a way that they should increase from left to right and should increase from up to down. So here I have only one table, 1, 2, 3. Here I have two possible tables, 1, 2, 3, and 1, 2, 3, and here I again get only one possible table. So here D is equal to 1, D is equal to 2, and D is equal to 1 again. And so on. For any partition, for any Young diagram, I can calculate the number of these possible standard tables with the help of, for example, a Hooke formula or something like this. There is a combinatorial formulas which allow one to calculate this number. And so in these isomorphisms, I should construct in my Hecke algebra the linear basis of matrix units. Each such an algebra, matrix algebra, d lambda, is a linear envelope of the matrix units corresponding to the partition lambda, Aj, Aj from 1 to d lambda. This is a standard matrix units with a well-known algebra. So I should construct such elements in my Hecke algebra. And in order to do this, I introduced the so-called Euclid-Murphy elements. These Euclid-Murphy elements generate the maximal commutative subalgebra in my Hecke algebra. And by definition, in Hn of Q, I have n such Euclid-Murphy elements. G1, by definition, is equal to unit element, and G2 is equal to G1 squared, and Gk is equal to Gk minus 1, Gk minus 1, Gk minus 1, for k greater or equal to. These elements are commute with each other, and they form the maximal commutative subalgebra. Moreover, their sum, G1 plus Gn, this element is central element. It commutes with any generator. And this element generates the whole center of the Hecke algebra. That is, any polynomials of Zn are central, and vice versa. Any central element in Hecke algebra can be presented as a polynomial in element Zn. Then I can construct, due to the fact that these Euclid-Murphy elements are commutative elements, commute with each other, I can construct inside this commutative subalgebra the common eigenvectors of these commutative elements with respect to regular representation. I'll consider the Hn as a finite dimensional space of representation of my algebra, and consider the left or right, it's all the same, regular representation. Any element acts by the multiplication from the left. So I can construct for any lambda A, it is a diagram, it is a table, one of the tables corresponding to the diagram lambda. I can order these standard tables, for example, in lexicographical ordering or somehow else. And this is a number of my table among the tables of the same shape. For example, this table I can, to this table I can assign the index 1, lambda 1. To this table I can assign index 2, and so on. And such elements or primitive idempotents can be constructed explicitly for any lambda a. I can construct p lambda a as a polynomial of Euclid-Murphy elements. This is an explicit polynomial in these Euclid-Murphy elements, and I will also denote this
kind of Schur polynomial.
sorry?
Kind of Schur polynomial.
Schur polynomial?
Yeah, I just wondered because the Schur polynomials are also associated with Ewing diagrams.
Yes, the Schur polynomials it is not a Schur polynomial. I'll give some construction, but the Schur polynomials are closely connected with the characters corresponding to these lambda diagrams. And any Euclid-Murphy elements acting at this primitive idempotent, I call this idempotent primitives because the square of each such idempotent is equal to this idempotent again, and the sum of this idempotent over all partitions and over all A from A to d lambda is equal to unit element of my Hecke algebra. And for different partitions and for different A inside one partition, they are orthogonal elements.
So these polynomials are polynomials in Euclid-Murphy, not in these sums of Euclid-Murphys.
No. They are commuting but not central.
I mean, no. I mean Z1 to Z2 Zn. Because well, in symmetric groups, Euclid-Murphy are just sums of positions.
Yes. You can find the connection of these elements to the elements in the symmetric group by the following simple operation. I should subtract 1 and then divide by q minus 1 over q, and then take a limit q to 1. Then, due to the Hecke condition, this fraction turns into the sum of elements which is used in the theory of symmetric group. And what is important for me is that if I multiply such an idempotent, yes. For example, which is the eigenvalues of Euclid-Murphy elements when acting on this polynomial? If I, for example, take some gk and acts on p lambda a, I have q to the c of k p lambda a if the number k is contained inside of lambda, because the lambda can be less than
what are those
P lambda a, it is a primitive idempotent corresponding to partition of n.
So in other words, we are the common diagonal basis for all Euclid
Yes, of course, because they're commuting, I can find the.
This P lambda precisely this.
Yes, this is precise the eigenvector of all Euclid-Murphy elements.
Are there formulas in terms of some more standard notations? I wonder.
What is the CK here? I should take the table lambda A, precisely this table, and should find the box where the number K stands. Then let us suppose that the i's row and j's column. Then C of K is just the two differences of J. Let us put here the index K. JK minus AK. This number is also called the content of the box containing the number K. So, in order to visualize these eigenvalues, I can write.
So P sub lambda is what is P sub lambda?
This is an idempotent corresponding to the Young table lambda A.
Not to the table, not to the diagram, right?
Diagram defines the shape.
Yeah, lambda
The
is
A,
diagram.
lambda is diagram. A is one of the tables.
So for every table there is an eigentable.
Any table is characterized by some placement of numbers.
I mean, the representations are defined by shapes, aren't they?
Yes, yes. The matrix algebra,
Defined by shapes.
yes.
Not by diagrams.
Not by diagrams, because any irreducible representation is defined by concrete diagram.
Not by shape.
Concrete diagram of the corresponding shape, because any representation defined by the shape contains in the regular representation as many times as is dimension. So any such table defines the column in the matrix column in the matrix n by n,
I see. So
and all of them are equivalent to each other.
just wonder whether if you take standard representation of a Sn by permutations of
Yes.
centers,
Yes.
then inside these representations you can also find irreducible. Is there a way to describe reducible representations inside this using this same technique or not? Is it true that if you take, say, P lambda A and multiply by this element,
I should take P lambda A, it is a concrete polynomial, and should consider the left ideal, Hn of Q.
right?
This ideal should be finite dimensional irreducible representation. If I take the same shape but some other table and consider analogous ideal, I'll get equivalent representation.
Yeah, right, but I need to find some representation inside the standard representation by permutations, for instance. If I want to take a representation of a Sn by permutations of tensors.
Yes, you should use the. I will speak about the R matrix representation in a couple of minutes. Of course, this representation now will be reducible, but I can subtract some representations by R matrix representations of these polynomials. my eigenvalues can be placed here in the following q squared, q to 4, q to 6, q minus 2, 1, q2, q minus 4, and so on. And if you write here some concrete diagram, lambda, then you can get the quantum contents of this diagram, and should calculate any eigenvalues of Euclid-Murphy elements. For example, G1, which is equal to 1, always has, because the number 1 is always stands here in the left upper corner, so G1 is always has eigenvalue 1. It is not surprising because G1 is unit element. G2, then I can place 2 only here or here. So Euclid-Murphy elements G2 has eigenvalues q to the q square or q to minus square, and so on. And for example, let me give some explicit examples. Of such elements. For example, n is equal to n is equal to 1. I have only one box, so I have only one idempotent which is equal to 1. N equal 2. I have such partition and the only Young table, and we can see can write G2 minus Q squared divided by Q to the minus 2 minus Q squared.
What is CQ? You said that
CQ, this CQ, C of K is twice difference of J minus K. J is the Q column, I is a row. So I write here all Q to this, Q to the C is written here. So here the condition G2 P1 2 is equal to Q to the minus 2 P1 2 is just it is a direct consequence of Hecke condition, because this I can simplify this expression to the following form: Q minus G1 over, this is a Q number, and let me point out why I should require that Q is not a root of unity, because I have such denominators each time, and in order to have a normalized projectors, I should have a right to divide by this difference, and this difference should not be equal to 0. So if Q is root of unity, then at some stage I cannot construct such projectors, and semi-simplicity of my Hecke algebra is broken, and the isomorphism with the group of symmetric with a group algebra of symmetric group is also broken. So this is a analogous formula is for such diagram, and I'll write, for example, for the n equal to 3, for example, which is a primitive idempotent P corresponding to such table. It is it is equal to the following: G2 minus Q2 minus 2, G2 minus G3 minus Q to the 4th power, divided by some normalizing multipliers. And again, we see here that we need that Q to the natural number should not be equal to 1. And the primitive idempotent has practically the same form, but some powers of Q are different. Minus Q to the minus 4. And here I have Q to the minus 2 minus Q2. Now Q to the 2 minus Q to the minus 4. I have written in these explicit forms in order to show you how to find.
What is the P on the second diagram on the bottom? Do you have a formula?
For this one? For this one I have G2 minus Q to the minus 2 divided by Q squared minus Q to the minus squared. And here I'll get immediately that if I put these elements together, I get just a unit element. Because this element is equal to 1 over Q plus G1 over 2Q. If I simplify the Eutis-Murphy element, G2 is just a G1 squared. If I use the Heike condition, I can simplify this element to this one. And so they are orthogonal to each other because if I multiply this by this, I'll get the Heike condition. And if I take a sum, I'll get just 1 due to this definition of Q number. These two one-dimensional representations of my Heike algebra, dimension is equal to 1, H2 is equal to 2. I have two one-dimensional representations. Because, for example, G1 multiplied by minus Q 1, 2. This is alternating representation, and G1, this is the only generator here, multiplied by 1, 2 is equal 1 over Q. I'm sorry, 1 over Q here and Q here. And let me denote this element by the formula E11 of the form, and this element by E22. These polynomials will play the role of matrix units of two-dimensional of the matrix algebra 2 by 2, because H3 has a matrix structure of the following form. The one-dimensional matrices corresponding to such partition, two-dimensional matrices corresponding to such partition, and one-dimensional matrices corresponding to such partition. 1, 4, and 1, 6 elements here. And these elements, the basis of these matrices and these matrices are just a primitive idempotent. Here I have diagonal elements of this form, so I need only the elements of the type 1, 2 and E2, 1. I should explicitly construct these elements and should prove that this indeed the matrix units. They satisfy the algebra of matrix units. And this can be done in any dimension explicitly. And I write here some identity. What can I erase now? Maybe Gosha, can I erase the left part of my?
I think there is an extra minus in the first idempotent. There is, I think there must be q to the second power.
Q to the minus 4, q to the 4.
First,
This is a 4.
yes, and in the denominator minus, not minus 2 but plus 2. No?
Here?
Yeah.
No. I should write here all possible eigenvalues of G3.
G3
minus 2. Minus 2, this is the eigenvalue of G3, and here G4 minus 2 and G4. And here I have G2 and G minus 4. No, this formula is correct.
So I used to think that if the eigenvalue of new Smurfy element is
you see, if you consider the recurrence procedure, how to get such idempotent, you should start from this 1, 1, 2, and should see where you can place the number 3. The number 3 you can place either here or here. In order to get the standard table, you can place the number 3 only here or here. So the possible eigenvalues for number 3 here is q to the 4th power, q to the minus 2.
right? Yes.
Yes. And if you put 3 here, as it done here, I should subtract another eigenvalue. And in the denominator, I should put the eigenvalue corresponding to this place, minus q to the 4, corresponding.
So in other words, there is a rule.
Yes, there is a well-defined rule how to construct these elements, and this is described in the paper by Pyatov Agiyevetsky, how to construct these idempotents in any dimension. All you need is an explicit form on the Young table, and so the explicit number of all possible eigenvalues, then this polynomial is restored without any problem. So the non-diagonal matrix units are defined by the following identity. Can be you see, for example, in the in the theory of symmetric group, you know that if you have a Young projector corresponding to the Young diagram, to the Young table, and two projectors corresponding to different tables but one the same shape, are connected with each other by just by multiplication, by some permutations, which maps the one table to another table. This quantum formula with Q is a Q generalization of this rule. And at this level, this formula has the form. If I multiply the table, the 1, 2, 3, in order to exchange 2 and 3, I should use the generator G2. Generator G2 is analog of P23. And any JK is analog of K plus 1. So here I should multiply by G2 plus Q to the minus 2 over Q2. This number is defined by the length of the hook connecting this element and this element. So I have here three boxes and should subtract 1 and get this. And this identically equal to the 1, 2, 3 multiplied by G2 minus Q squared over 2Q. Identically equal. So this combination will be denoted by, for example, if this one, E21 with some element alpha. This is a number, normalizing factor. Because this operator and this operator are practically inverse to each other. If I multiply them, G2 plus Q minus 2 over Q2, G2 minus Q2, I'll get the unity multiplied by 1 plus 1 over Q2 squared. So I should normalize this. I can normalize these elements in such a way that these two idempotents are connected with each other by similarity transform. So this polynomial is of diagonal elements. Another of diagonal matrix units is defined by analogous identity. What? If I put this one here, then I should put this one here, and I'll get another matrix units. And the defining properties of these new elements is that, for example, if I take G2, if I calculate G2 over E11, I'll get here Q squared E11, G2 acting E22, I'll get Q to the minus square E22, and this element behaves like G22 when multiplying from the left, and as E22 when multiplying from the left, and as E11 when multiplying from the right. And moreover, they do satisfy the good algebra of matrix units. If I calculate Ij multiplied by Ks, for example, I'll get just the usual algebra Is. Of course, if I'll take at last, if I'll take the sum of this of this primitive idempotence, I'll get a central element corresponding to the direct summand in the decomposition of my Г.И. algebra. Let us define this projector without any numbers, which is just the sum of all tables. And it can be proved that this is just Z3 minus Q to the 3 and Q number 3, Z3 plus here Q minus 2 and here plus minus Q squared 3Q and divided by some Q numbers, which is normalizing elements. This is a central element. This is not primitive idempotent, but central idempotent corresponding to the direct matrix summand corresponding to this shape.
If I get it, G2 plus G squared divided by 2Q, Q squared divided by 2Q, isn't it just Q, 1/2 of Q? I mean, on the left. If I get the formula.
This is off-diagonal matrix
Yeah,
unit.
I mean, the second term in this formula looks a little bit artificial, because when you divide Q squared by 2Q, you just get.
It's quantum 2.
Sorry?
It's quantum.
It's not 2Q, it's quantum 2. I'm sorry, just didn't see the difference.
This is a small q.
Yeah.
This is q number. Kq is equal to q to the kth minus q to the minus kth, q minus 1 over q. So I'll get the whole matrix structure. This is these matrix units form the linear basis in my Г.И. algebra, 6-dimensional for the n is equal to 3.
I'm sorry, I didn't get. Why do they call these products of diagonal matrix units? We define this to be diagonals. And
By definition, I'll take this primitive idempotence as diagonal matrix units. Why? Because they take part in the decomposition of unity, and they are orthogonal to each other. And if I consider, I'll get the two-dimensional representation if I consider the ideal H3, for example, over this space is two-dimensional. And here I have generators G1 and G2. Let us consider what I'll get if I try to construct such an ideal. G1 is always G1 acting on these elements get a number, Q number. This is Q to the 1, 2, 3. And G2 over 1, 2, 3 is independent by basic elements. And it's very easy to prove that when I multiply this element and this element by any element of my Г.И. algebra, I'll get a linear combination of this one and this one. Two-dimensional representation.
okay, then why we have to subtract something to get something canonical? I don't understand why
Yes.
particular this expression.
Why particular? Because this expression, it is just a linear combination of this basis vector and this basis vector. And it is this linear combination satisfy this property. I should get something which behave like a matrix units, not in independent basis, but it should behave like matrix units. Of course, if I consider just a representation, I can take two independent elements and it is sufficient.
So sorry, just to clarify the formula, G2 plus this expression is the E12 corresponding to the diagram.
This is E11 and
The whole product times this expression. So what is E22 again? What is E12?
E12, it is the whole this product. Let us E21. Because if I multiply from here to the G case, I'll calculate this G case on this diagram and get all the eigenvalues of G case corresponding to this diagram. If I multiply this element from G case from the left, I should use the identity and I'll get from the left another primitive idempotent. And multiplying from the left, I'll get another set of eigenvalues corresponding to another primitive idempotent. So this whole product is my off-diagonal matrix units. If I have a greater dimension, of course, I'll get here not only one such a linear product, but maybe two product, three product. It depends on how many transpositions I should apply in order to reproduce another Young tables for example, from the given one, from the first table. Here I have only two tables, but for example, if I consider the greater, 1, 2, 3, 4, 5. Here I have 5 tables. So I should replace somehow these elements between each other. And in order to get this off-diagonal units, I must here have here 4 off-diagonal units. Some of these off-diagonal matrix units will get several such multipliers from one side. So this is a matrix structure, and this is very important in the representation theory of quantum matrix algebras corresponding to the Hecke R matrices. So let us say about the R matrix representation. Now, if I have R matrix R of some form n squared of some size, this matrix satisfies the braid relation and Hecke condition. If I have such R matrix, I can define the R matrix representation of Hecke algebra Hn. Let us consider the finite dimensional space of dimension n. Then I can treat this R matrix as a matrix of operator in tensor square of V. I'll fix here some bases, xy, xj, and I can treat this matrix as a matrix of operator acting in this tensor square. And then I can represent my Hecke algebra by the following map. generator Gi is maps to this copy of R matrix.
So but this will correspond to some representation of the symmetric group.
Yes, this is like a tensor representation of symmetric group, but permutations of basis vectors.
So is there a way to identify elements which, I mean the elements within this representation in terms of symmetrical? I mean here you have representation by R matrix.
No, it's very complicated identification. You should identify them through the matrix units.
Yeah.
You can construct matrix.
Direct way, right? No direct way.
No, not direct. If I erase here this line, I'll get, of course, the representation of symmetric group. But if I try to construct the R matrix from the P, it's not so easy. This is an R matrix representation, and for me, very important will be the following elements. Here I have an idempotent corresponding to the 1 column diagram. This is an analog of Q antisymmetrizer. And it can be proved this antisymmetrizer, Q antisymmetrizer, has a very efficient form, very efficient for all calculations. It can be represented in a factorized form in the following way. I'll get the series of Q antisymmetrizers. Here I have an antisymmetrizer Q to the K minus 1. And here again K minus 1. 1 over K minus 1. This element acts in the first copies, in the first K copies of my tensor product, and the indices of the last K's copy is contained only here. Graphically, I can represent this antisymmetrizer in the following way. If I have an object 1, 2, K, it is equal to the previous object 1, 2, K minus 1. Then I have something K minus 1, K, and again 1, K minus 1. The structure of this formula is in the following way. And this is very convenient and very powerful formula which makes all the calculations very efficiently. So, of course, if you take the Q to 1 limit, you get here the factorized representation of the total antisymmetrizer in the symmetric group.
Here we just get some element in symmetric group which goes to this and this very strange operator, right?
Very strange who?
I mean operator A, K.
Why it is very strange?
Well,
It is.
Write it down in terms of the standard permutations that will be pretty messy, I'd say.
Okay. And for us, the important thing will be the following: definition. And we will consider the R matrices only of these types, of this type which I'll define. The G, L, N type R matrix. We shall call the R matrix of this size satisfying the Hecke condition the G-alien type R matrix if the higher order antisymmetrizer is a rank 1 projector. Rank A1 is equal to 1, and the next projector is identical 0. If we have such situation, we shall call this R matrix the G-alien type. The G-alien type R matrix, for example, the well-known Drinfeld-Jimbo R matrix, which is connected with the quantum groups of the AC series. But of course, the Drinfeld-Jimbo R matrix is only an example. For example, the Kramer-Gervais R matrix is also G-alien type. And I'll consider only such type R matrices. And the next very important property, not erase antisymmetrizer. Yes. Let me write down the consequence of this requirement. If this is an element, Hn, An is a matrix of operators in such space. No? So this matrix can be characterized by n A1, An lower indices and J1, Jk, Jn upper indices as an element of this of this algebra. And due to the rank of this An is 1, this matrix can be presented as the product of U of two tensors, U A1 An, V J1 Jn. It is a direct consequence of this requirement. This is a rank 1 matrix, can be represented as a product of such tensors.
What are U and V?
U and V, some tensors which depends only of the lower indices and upper indices. If Q tends to unity, here I'll get just U is just a totally antisymmetric tensor of Levi-Civita tensor when I use the physical terminology. This is a structure of rank 1 projector.
And the fact that A n plus 1 is equal to 0 is a consequence of this assumption, right? If the rank is equal to 1, then the next projector is equal to 0.
Yes, the matter you should write. You should read these conditions from opposite direction. First, I'll require that the n plus 1 is equal to 0, and the second, I'll require that the previous projector has a rank 1, because you can have here, for example, not 1. There is various examples which destroys this condition. Of course, there is matrices for of the super matrices, GLMN type. For these matrices, the set of these projectors is not equal to 0 at any n. you can construct the antisymmetrizer of arbitrary length. This is, for example, if I consider the simplest example, Q 0, 0, 0, lambda 1, and I put here Q, this is an example of GL2 R matrix. But if I change here minus 1 over Q, this is a G11 R matrix. And for this type R matrix, I can construct the antisymmetrizer of any order. Here I'll get 0 if I try to construct such like idempotent.
Why don't you write the indices below? I mean below the A, because
Here?
No, by A, by A.
Ah,
Here. I mean in the definition on the right hand side, you use indices.
this object lives in the first n copies of the tensor product. If I if I write here n, so here I should write the sequence of n indices, not obligatory from 1 to n. Maybe from 2 to n plus 1, and I can embed this antisymmetrizer into the tensor product in many different ways. So GLN type R matrix satisfy this requirement. And then the definition of skew symmetric R matrix, it is also very important for us, but it can be proved. It is done in the one of the work by Dmitry Gurevich, that any GLN type R matrix is skew invertible. What is a skew invertibility? You know that all our R matrices, due to the Hecke condition, they are invertible, which means that R minus 1, 1, 2 multiplied by R1, 2 is equal to unity in the first and the second space. So here I have just a matrix summation of the form R minus 1, A1, A2. Here I have alpha 1, alpha 2. I'll get, I take a summation of these indexes, A1, A2. And here again, three indexes, G1, G2. They're just delta A1, G1, delta A2, G2. This is a usual invertibility. And skew invertibility is the following thing. There exists a matrix psi of the same size as R. And we have the following condition. Trace in the second space of the product R1, 2, psi 2, 3 is equal to trace of the second space psi 1, 2, R 2, 3. It is just a permutation operator 1, 3. This is a skew invertible. Very strange and very useful condition. What is written here? Let me visualize this condition in matrix indices. I have in the first space, I have three indices: I1, G1. Then alpha, beta, psi, beta, alpha, matrix summation, and trace is taken. And here A3, J3 is just PA1, A3, J1, J3. Так. Ага. Less than 10% of the charge is left. I think that maybe I will be in time.
How much material do you have to?
Вначале у меня было 40%.
Сколько еще осталось?
10.
Сколько еще осталось читать?
Ну, я думаю, ну, я не больше. 10-15 minutes. Of course, but... это... И, слушай, это будет у меня дополнительно... Yes, this is a power bank. Дополнительная штука, которая будет висеть. Ладно, пока это не очень удобно, потом, может быть. It's just delta A1, J3, delta A3, J1. This property is called skew invertibility. And any GLN type R matrix is skew invertible. And with this matrix psi, we define two very important n times n matrices. Let me define B1. This is a trace psi B2. 1, 2, trace of the first space. So Bij is just sum over alpha, psi alpha alpha Aj. And the matrix C1, trace over the second space. So Caj is equal to if I have such matrix psi, I can define such n by n matrices. If if one of them is non-degenerate, then the second one is also non-degenerate. If that, for example, that C is not equal to 0, then I have an identity B over C is a unit matrix Q. They are mutually invert to each other. And this matrix plays an important role in the representation theory of quantum matrix algebras, which is defined by this R matrix. And this one, this matrix defines the so-called R trace or Q trace. The Q trace should replace the usual trace when we will construct the center of quantum matrix algebras, which is a quantization, for example, of universal enveloping algebra, GLN. Definition, trace R of any x, x is n-to-n matrix. Any matrix, and this is a just usual trace, but C multiplied by x. This is very important definition.
What is so special about this trace?
It will be clear later, because this trace in quantum matrix algebras, it is R trace, which should be used in order to get the central elements.
Okay, if you take just the elements in the representation of Hecke algebra, right? Say this, you take this matrix representation of Hecke algebra.
Yes.
Suppose this algebra is actually, well, our matrix is, what do you say, virtually of skew invertible something. So you have this skew trace.
For example, if I GL2 R matrix, Q it's not difficult to construct the psi explicitly, and C is just 1 over Q, 0, 0, 1 over the Q to the square. So I have here just the weight. This is element for this case. This is x11 divided by Q plus x22 divided by Q to the 3 power.
But what are the properties? Usual trace has the property that when you take x times y, you take the trace and it's equal to the trace of y times x. So what is the property here? Because usual trace has this crucial cyclic commutation property.
Yes, here the if you has if the matrix elements of X is non-commutative elements, you do not have the property of cyclic permutation.
Yeah, sure.
But the very important property is the following: the matrix C satisfies such a property. So if I have a multiply trace R 1, 2 case of some object living in 1, 2 case space, and here I have any polynomial of R1, Rk minus 1, I can cyclically move. This trace in this is a here.
R1, R2, R3, what are they?
This is a R trace taken
On the right.
polynomial, some polynomial in R matrices.
Ri's. Are they I, comma, I plus 1?
Yes, of course. This is just a short notation for this.
What will be equal to?
So the polynomials in R matrices I can cyclically move inside of this R trace.
So what will be equal to then?
It is equal to the same when polynomial stands in front of X.
Oh, I see.
Because this here trace from 1 to case, and here I have a chain of C matrices, C1, Ck, then X, then a polynomial.
For any matrix x1,
And due to this property, I can just move the polynomials through this C.
for any element x,
For X doesn't matter here. It is just stands. It is a sum matrix.
What is C2? I mean, what is C2?
This is a matrix with commutative elements, so C2 is just one tensor C. C2. It is our standard matrix notation.
so it is equal to polynomial of Ri's standing on the left.
Yes, it's a very important property which allows us to make all the calculations. It's sufficient. When I will operate with quantum matrix algebras, I will use this property very intensively.
So it doesn't depend on the polynomial, right? It doesn't depend on the polynomial, right?
For any polynomial.
Any polynomial.
Because any R matrix,
So again, can you write it down explicitly? Trace R trace in the length directions 1 through k of x1 so on k
yes, 1 over k.
is equal to what?
this is
So what you have written is just the same.
R trace is just an explicit definition. What is a multiple of R trace?
But what is the equality? What is the crucial, what is the cyclic permutation equality? Trace of...
Yes. And then I should write this as trace
Yeah.
1 over k, C1, ck, polynomial is standing here, and then x.
This C1, CK, they're just R traces.
Yes.
So
The chain of C is an attribute of R trace.
it's just definition of R trace, so you can actually...
Yes.
yeah.
And I can cyclically move this polynomial to this place. It does not depend on any properties of C. But then I should move this polynomial through the chain of C to the x. And this require this property require this condition for C.
Reference.
Hmm?
Can you give a reference
For what?
for this?
Or this is. I do not remember precisely because this is very common knowledge of all this of the science. But I can recommend you, for example, the papers by Oleg Givetsky, uses of quantum spaces. And this is rather long ago in 19th. В общем, в 90-е годы это все развивалось, и вся эта технология была найдена. This property is not very difficult to prove. You should use just the definition of psi and the property of the braid relations on R.
Yeah.
If you use the braid relation on R, you should.
Is it true that when you go now to the limit with a q equal to 1?
The q equal to 1 is not very interesting because this is just unit matrices.
I mean, you have this for arbitrary x, right?
Then I'll get just the usual property.
But then there is arbitrary x. Oh, I see.
It doesn't depend on the x. Because here I have a trace, so I have cyclic permutation in any case. But in order to move this polynomial through this C,
I just wonder what is so important, because this polynomial of R1 and K, isn't it just a polynomial of matrices with commutative
yes,
entries?
yes. But you see, I should write. I should explain you. For example, trace 1, 2, x, for example, R1, 2, R trace. And trace R1, 2, R1, 2, x. What is the difference of these two things? This is by definition trace 1, 2, C1, C2. It is always first I write C1, C2. X, R1, 2. And here I should trace 1, 2.
X1 or X2?
X1, 2, X1, 2, R1, 2. C1, C2, R1, 2, X1, 2. And it is not obligatory equal to each other.
If you erase C1, C2 from the notation, you just get the usual property of the trace, right?
Yes.
Okay, so I see. So it turns out that actually have a little bit more, right?
Yes. And then in order to equalize these two expressions, I should require that R matrix can be moved through the chain of C1, C2. Because this is of course is equal to trace 1, 2, R1, 2, C1, C2, X1, 2. This is just the Что?
What should be commutative?
This equality is just the usual cyclic permutation property. But then I put R here. This can be done for any R matrix, for any C, for any X. But in order to get this form, which is equal to this by definition, I should require that the R matrix comes through the C1, C2, through this chain. And then, due to the property trace 2, R1, 2, C2, 3 is equal to P1, 3, immediately we get the following trace. R trace over the second space, R1, 2, is equal to 1. Okay. Наверное, мне стоит уже остановиться. Yes. The next topic will be the following non-commutative algebra, where R1, 2 is a GLN skew invertible, no, GLN R matrix. Next time I will explain how we can construct the commutative subalgebra inside of this algebra, how we can construct the invertible matrix, the inverse of T minus, and then it allows us to define the antipode and the Hopf structure inside of this algebra. Then we can define the determinant of this quantum matrix algebra, and factorizing over this determinant. Determinant is a central element. I'll get the algebra of quantized functions on the group SLN. This is a short plan for the next time. And in so doing, I will use the properties of GLN skew invertible R matrix.
Okay, I think since there is nobody here listening to this talk, I think it's time to stop it. Maybe there were no questions, at least I have none. I have asked everything I wanted. Okay, if there are no objections, I stop the broadcast. Я думаю, что мы на самом деле остановить трансляцию. Было много.
Это было половина того, что я хотел сегодня рассказать. Нет, но тут все зависит от того, к чему мы стремимся. Если мы просто хотим это.
У меня очень простой вопрос. Я хочу посмотреть вот эту вот алгебру Гекке, это же то же самое, что алгебра перестановок, алгебра группы перестановок.